Hello, today I'm going to talk about the interval universal approximation for neural networks. This is a joint work with us, Gautam and Somesh. So let's get started. Neural networks are widely used nowadays. It's used as spam detectors, as image classifiers, and also used in autonomous driving. So given the predominance of neural networks, it's important to understand the security of those systems. Unfortunately, people have found that neural networks are extremely vulnerable to adversarial attacks. So what are adversarial attacks? So given an input, if we add a small perturbation, the classifier can change its predictions significantly. In this panda example, if we add a noise to it, the result image is still a panda to human eyes. However, the classifier will say this is a gibbon instead of a panda. This raises serious concerns for users. We would like neural networks that are robust against those adversarial attacks. The problem is there are exponentially many perturbed inputs, and it's impractical to execute all of them. So one solution is that we can interpret the perturbed inputs as a single abstract input. So instead of a point at each dimension, now we have high dimensional intervals. So we'll consider abstract interpretation. And the good thing about abstract interpretation is that we can actually achieve certified robustness. The idea is kind of simple. We want to over-approximate the values of the functions. And in fact, neural networks are just a composition of if operations and hidden layer activations. So we only need to define abstract operators for those operations. So for example, if we have to define affine operations, we only need to define the operators for multiplication and additions. So for example, if we have 1, 2, 2 and 2, 2, 2, those two intervals, if we want to add them together, we'll have 3 to 4. For commonly used hidden layer activations, such as ReLU and the sigmoid, they're actually monotonic. So this is good because the abstract operators for them is very simple. We only need to evaluate both ends of the interval. So now it's very efficient to execute exponentially many concrete inputs. The problem of abstract interpretation is that it's sound, but it's not necessarily complete. So by complete, we mean that the result of the abstract interpretation reflects the actual execution of the concrete function. So for example, if I have a function x minus x, and the input domain is 0 to 1, the result from abstract interpretation will be -1 to 1. However, x minus x is always valued to 0, so the result is very imprecise. Now the problem is we might have a neural network whose inputs are always robust, but we cannot certify them use abstract interpretation because abstract interpretation is so imprecise. So this raises the following research questions. So can we have a robust neural network whose robustness can always be certified use abstract interpretation? And the second question is, if the answer to the first question is yes, how hard is to build such a neural network? This gives our main result, which we call interval universal approximation. We will answer the question from the perspective of approximation theory. So given a target function, we can build a neural network that approximates it using any practical activation functions. And now the neural network is not only accurate, the robustness can also be certified using abstract interpretation. So this is a positive answer to the first question. The answer to the second question is kind of negative. It is computationally hard to achieve such an approximation. So if you want to know more details about our result, please check out the following link. Thank you.